Hi, and thank you so much for inviting me to speak in your workshop. What a great lineup of speakers and topics, and what a wonderful opportunity to come together as a TCN to think about these really important issues. I'm Libby Ellwood, the IDIG Bio Director of Education, Outreach, Diversity and Inclusion, and Global Collaborations. And today I'm going to be speaking about the importance of FAIR in biodiversity science and research. While many scientists and researchers have been following versions of FAIR principles for a very long time, it was this article published in 2016 by Wilkinson et al. In Scientific Data that laid out a framework and best practices for scientific data users. Leading up to and since the publication of this article, a number of working groups, societal and organizational committees, additional publications, and even an NSF-funded solicitation for research collaboration networks have emerged, all focus on best practices surrounding FAIR principles. I think it's important to go right to the source of these best practices. And so for much of the material I'll be referring to, you can also visit them at gofair.org. So I have the website there at the bottom. So what is FAIR? FAIR is an acronym for findable, accessible, interoperable, and reusable, which was developed to improve the ways that science is done, particularly in our current machine-oriented workflows and data flows. That is, while human may be able to decipher and pull together and link different elements of a related topic, it is often the case that our computers require us to enact specific operations in order for a task to be completed. Further, it's often the case that enabling computer-driven steps is also beneficial for humans and the overall efficiency of our work. So no matter how you look at it, it really is beneficial. I'll define each of the elements of FAIR here, then we'll go into some more depth and provide examples in the slides that follow. First, findable. In order for our data to be the most usable for a wide variety of purposes, they need to be findable by both humans and computers. And a necessary part of this is having metadata that are machine readable. Next, data need to be accessible. Once you find the data, you need to be able to know where and how to access them. This may include authentication and authorization. Data need to be interoperable. Data are most valuable when they can be integrated with other data. Most analysis and workflows involve more than one kind of data, so it is therefore critical that your data can play well with others. And of course, reusable. In order to truly advance science, we don't want to be reinventing the wheel. When data that was collected in the past can be used for current and future analysis, it enhances and advances research, in addition to being sound scientific practice. So going through each of those in turn, one of the key elements to ensuring that data are findable is making sure that they have a globally unique and persistent identifier and that their metadata are rich, include an identifier, and are registered. This example to the right shows the importance of identifiers being used to be able to link the different types of data, with the physical specimen being at the heart of the model. So there, towards the upper middle there, you see a light green box with a grayish blue box in the middle called physical specimen. And each arrow out from that specimen leads to a different item that refers to, made use of, or is based upon the specimen itself in one way or another. For example, this specimen has sequence data associated with it, so you can see that link out to the left. It has images and publications, and even another institutional identifier. All of these digital data follow this framework that allows data users to find data from any point. So maybe I am most interested in the specimen and all the things that are associated with it. Having these identifiers and making all of this findable allows us to see the full suite of information associated with that specimen. I could also enter this workflow from any of the other nodes. I could be interested in the sequence data and then lead back to the specimen or the publication or the images or anything else. And this is all thanks to those identifiers and their ability to link these data and make them findable. So imagine we had a bee specimen here in the middle, and all that can be linked out from it. In addition to the example linkages here, like the sequence data, images, publications, maybe there's a host plant, a parasite, an insectivorous predator species, or other associated species. Each element there can have its own data and metadata and identifier that can be linked to the original physical specimen. Identifiers are also critical for making data and metadata accessible, even when the data themselves may no longer be available. While the common recommendation is for data to be as freely available as possible, sometimes authentication or authorization is necessary. In Europe, for example, a survey of 115 natural science museums found over 100 commercial and in-house solutions for managing collections. So you see that quote on the right. Current sets of digitized specimens and related information are held in various collection management systems with widely different functionalities and management approaches. A recent study from Craus from 2018 that was unpublished across 115 European natural science museums shows more than 100 commercial and in-house solutions are in use. So maybe that sounds a little bit familiar from your own work with the TCN or with other institutions. But as we move towards increasing connections among collections, these systems all need to be considered. In many cases, the numerous systems can remain as long as they're each following agreed upon methods for data accessibility to ensure that data are available and that when the data are accessed from numerous sources, that they are standardized or standardizable. So a similar example would likely be given from just about any TCN. And while I guess that there aren't over 100 collection management systems and operations in Big B, I would guess that still there are numerous systems, each with slightly different modes of accessibility. Next, we have interoperable. Imagine we've just downloaded data sets from several collections in that European study, or even from several of the Big B institutions. In order to address questions like those listed here, who has published about a certain bee species, what papers have used materials from a collection, what bees are living at a given location, the data need to be interoperable. And interoperable doesn't necessarily mean identically formatted or containing all of the same variables, but it does mean that the data need to be able to work with each other. And that includes using a common language, perhaps an ontology or shared vocabulary that follows community standards. To support scientific advancement, data need to be reusable. This includes rich metadata and attributes that are released with a clear and accessible license and with detailed provenance. Data also need to follow community standards. The figure on the right there shows how a researcher may approach a new project. At the top, we enter the diagram with a problem or research question. One of the first steps the researcher will take will be to find data and associated information from past work. This will help inform their current work. And they may decide to directly incorporate, that is, reuse those data or derivative data in their current research. The more data that are findable, accessible, interoperable, and reusable, so following the full suite of FAIR principles, the researcher can use all of this to enhance their current work. This provides the best case for addressing the research question, especially given today's complex and in-depth research questions. Having the most data accessible to us, not just from within our own networks, but outside of them, and often globally, really enhances the work that we are able to accomplish. And then we enter the landscape of available data and knowledge with our own work. So it comes full circle in the end. So far, I've focused on FAIR directly. And while we need to follow these practices closely and to the greatest extent possible, there are instances where data should not necessarily be fully open or accessible to all, for example. And this is where a very different, though related concept comes into play, and that is called CARE, which stands for collective benefit, authority to control, responsibility, and ethics. CARE is especially important when we work with Indigenous or traditional knowledge and the data and information that go with it. The slides that cover the elements of CARE are derived from the Research Data Alliance, the RDA. And if you're interested in FAIR, CARE, and many other ways of thinking about data that are presented not just in this talk, but in presentations throughout this workshop, I encourage you to check out RDA, its website, and its working groups. There's a ton of information on their website, and IDIGBY is a member of RDA. So if you ever need assistance accessing information or other things about RDA, please just reach out. These figures from Jessen et al. From Frontiers in Ecology and the Environment show on the left the increasing use of Indigenous knowledge in a variety of scientific publications, with many focused on ecology and subfields therein. And the figure on the right shows applications of Indigenous knowledge in many different fields. So a few things to think about as these may relate to Big B. First to consider is whether you have collections that fall into this category of Indigenous knowledge. Does your collection have specimens collected on tribal lands or by members of local tribes? Are the species you work with, the bee species you work with, distributed on tribal lands? And might your research benefit from inclusion of Indigenous researchers? In this paper, Justin et al. Suggests that there's a lot that can be learned from Indigenous knowledge that sheds light on scientific research in unique ways. Likewise, they recommend that if you do engage with Indigenous researchers, that the process begin with building a relationship, human to human, build that human network, and not necessarily simply focus on data. I mentioned these points as they relate to care principles and hopefully following them in your work as well. I'll just quickly go through a little bit more information about each of the points in care. So C, the collective benefit. Data ecosystems should be designed to function in ways that enable Indigenous people to derive benefit from the data, so that it's not just taking the data for our own purposes that might not relate to their original purpose. A is authority to control. Indigenous people's rights and interests in Indigenous data must be recognized and their authority to control such data respected. So you'll see some overlaps even in the fair data principles, of course, with Indigenous peoples and Indigenous people's rights. Taking this into particular consideration as they relate to care is especially important. Our responsibility, those working with Indigenous data have a responsibility to share how those data are used to support Indigenous people's self-determination and collective benefit. And then E, ethics. Indigenous people's rights and well-being should be the primary concern at all stages of the data lifecycle and across the data ecosystem. And this comes back to that notion that we don't necessarily want all data to be fully open for any purpose at all, especially when it comes to Indigenous data. It's most important that we build the human relationships and determine what data might be most suited to answer our research questions and who best to include in answering those questions and which data to use. I will stop here. Thank you so much for allowing me to talk with you about some FAIR principles. I welcome you to reach out to me if you have any questions, and of course, follow iDigBio wherever you like. Thank you.